Okay, so that concludes our segment on the roundtable discussion. So now we're going to resume the technical program. And the next speaker is Raksim Bhattacharya from Aerospace Engineering.
Do you see can you see my slides?
Yeah, can you hit swap displays and can see your on the top left button? That's great, thanks.
Okay, yeah, this is a challenge. Now my audience screen is overlapping with my slides. Okay, that's fine. Okay, so I'm with the Aerospace Engineering Department, and one of my work is with my computational fluids colleague in my department, Diego Donzes, and this work is mostly done by the graduate students, Vedank and Komal, and we got a couple of NSF grants to look at generating finite difference schemes. But just to give an idea of what I do in general for future collaborations, my work is mostly in controls and dynamics and estimation. That's my formal training. And then I work on uncertainty quantification, mitigation, essentially working with stochastic systems. And then their applications could be, just propagation estimation and control with uncertainty. And then work on numerical algorithms and high performance computing to support this work. And so mostly I work with space situational awareness, predicting when collisions may happen, uncertainty on landing sites for planetary descents, robotic manipulations, and conventional aerospace applications. So today we're going to talk about scientific machine learning, and the focus is on solving PDEs. And PDEs have become very useful in modern engineering disciplines. Companies are going mostly for model-based designs, and they can explore what-if scenarios at a very high rate. They don't have to build prototypes, so it's less expensive to explore these things. Another emerging area is this digital twin, which happens post manufacturing. So you have a running system, and then you attach a digital model with each of the system, and then there's a lot of data that comes out during the operation of this system, any one of these. And then you refine the model to reflect a more accurate representation of the actual system in place. So then the model, it becomes a model of one, which is constantly growing with the system during its life cycle. So we refine the design. The main use of this digital twin is to predict the failures. That's one of the main reasons. Fault diagnosis, fault isolation, predicting when an airplane should be brought in for servicing. At the same time, it is also used to detect cyber attacks. So anytime there's an anomaly in the behavior of the actual system, it departs from the model, and that anomaly could be because of a fault or because of a cyber attack. So I'm kind of interested in digital twins, and then so we combine data fusion, sensor fusion with model prediction and model refinement, and PDs play a big role in that. Another major area that I work on is uncertainty propagation. So given a nonlinear system, you have uncertainties expressed as random variables and random processes that excite the system. So how does the state PDF evolve? And so that would be a Fokker-Planck-Kolmogorov equation, a PDE, and very high dimension, the dimension of the state space. So that PDE is a bit challenging because it's propagating the probability density function, and so that solution must respect properties of the PDF, meaning positivity, and integrates to 1. So it should be measure preserving, and positivity conditions should be there. So So many methods are there. The classical is this mesh-based methods in which you make a grid, structured or unstructured. So they can't handle complicated geometries, and so that led to mesh-free methods in which you just have points, and you choose some sort of a radial basis function or maximum entropy basis functions to construct the solution over the entire domain. So mesh-free methods are, I would say more advanced techniques than mesh, but depending on the problem, you choose the method that suits. Now, recently, machine learning has, brought in this capability in which a neural net is used. So what is, machine learning? It's really nothing significantly new, but it addresses an important problem where we have difficulty in representing. So in finite element, we will choose triangles and put a function, and there's something called HP refinement where you make the grid size smaller, or you use higher order functions like polynomials to approximate. In the mesh-free world, you have radial basis functions, and so there's this width parameter that you have to play with. Similar concerns are there in maximum entropy. Whereas in the machine learning, we don't worry about choosing that basis function. So the basis function is the real contribution. So that basis function is represented as a neural network. And then you apply data to learn. And data could be, from a solution perspective, you have a data. But from the PDEs, it's really solution error. And you compute the solution error across the domain. And then the machine learning learns, the neural network learns to minimize the errors at those collocation points. So it's essentially an L2, and the grid can potentially adapt as well. So there are some concerns here. I mean, it is showing a tremendous amount of success, but there's some concerns like, how do you enforce constraints and like positivity and things like that. Everything is clubbed as a cost function, which is most commonly an L2, but you could think of maximum entropy and things like that as well. So everything is converted into a soft constraint, and because it might be it's a non-linear programming, so your local minima, you'll get what you get. And so some of the concerns are that there are errors associated with all these methods, and so in the digital twin world, we need to quantify that error because we're going to make a decision based on the solution. So in mission critical applications, like if you're dropping something on Mars, in which I can't do real experiment, I am very heavily reliant on models. I need to quantify this uncertainty because the higher level design says this is my error budget in the system design. So this is the kind of fidelity I want from the models. And so a lot of work in uncertainty quantification is more in the classical mesh and mesh-free world, the computation mechanics folks. So we have the whole area of uncertainty quantification talks about that. When I solve something and I get a nice picture, is it physics or is it numerical errors? That understanding needs to be there because if I know the gap, then I can perhaps do a few expensive experiments to bridge the gap and refine my solution. So I think one of the main challenges in machine learning would be that quantifying the errors, because most of the solution is that I have a classical way of doing, here's a picture, and I am doing it with neural network, here's a picture, and I compare, and that's how. So I always seem to need a baseline to get confidence on my machine learning. So I think more research on directly quantifying the errors in machine learning would be useful. A lot of work has been done in that. So in this talk, I'm not going to be talking about neural network as a representation. I'm going to be talking about a mesh-based idea. So we're looking at a very classical approach, finite difference. We have all seen this. And then the novelty here is normally the finite difference schemes are chosen very ad hoc. You choose a central, you choose some favorite method, you throw it in, and you get an answer. But here I'm trying to present a work in which the finite difference scheme is generated specifically for that PDE, for that geometry, and for the initial conditions. And yes, I need an underlying mesh to define the finite difference, but the scheme, which is the coefficient of the finite difference, they are going to be optimized, or if you want to say learned. So the current approach in finite difference, you choose a temporal spatial discretization, mostly ad hoc, and the discretization is P independent. I mean, central, backward, forward. You have some knowledge, if you're propagating forward, then you want to conserve some property. So there is, it's not 100% ad hoc. There is some knowledge of the PD that goes in. And then we work with the grid size temporally and spatially to get the acceptable errors and stability. So there are a lot of moving parts, and you put together everything, and then you do an analysis, and you see, okay, this is what I'm getting. These are my errors, and you go back and you refine. So in this talk, I'm going to talk about a unified framework in which all these considerations are, put into as constraints in an optimization problem, and the finite difference scheme just comes out as a solution of that optimization problem. So this slide is essentially going to talk about, summarizes all, what I'm trying to say here. So you got a general PDE, in which you got a temporal operator and you've got a spatial operator. And you want to solve this numerically using finite difference scheme, okay? And so we're going to assume that there's a mesh, and then you're looking at the ith point. And so the fundamental challenge here is to approximate these derivatives based on the values of the solution at these grid points. And so you discretize the operator. So this stands for the dth derivative of f at the ith grid point. If you assume that it's a constant spaced grid, then delta x is constant, comes outside. And then it is some sort of a linear combination. So the derivative is defined as a linear combination of the solution at the ith points, or I plus m. And so you choose, 2 eta plus 1 points around the I. So for central, you would choose 1 point on the either side. So the 3 points would define the derivative. But in this case, I'm saying that, don't worry about central and don't worry about what the coefficients are. You choose some neighborhood of I from where you're going to pick up the solution and then multiply it by an unknown coefficient. These are the coefficients that are going to be learned or optimized for. In central, it would be plus minus half. But here I'm not assigning any value. And so then with all the derivatives represented in terms of linear combinations of the solution and an unknown coefficient, I throw all of them into a PDE. So in this case, I'm writing a generalized linear PDE with up to dth derivative. Now, when you plug in these coefficients or these approximations of the derivative in both time and space, you get a discrete time system, okay, where this matrix big AD is captures all the coefficients over the entire domain. So we get a discrete time system whose matrix, system matrix, is parameterized by this coefficient, which is unknown, and that is what I'm trying to find out. Now, those who have, are familiar with the control systems background, you look at this as a discrete time dynamical system, and this is, in some sense, a controller, a game that needs to be designed to achieve a certain behavior of this discrete time system. This discrete time system, in our case, is a numerical algorithm. So we are treating this iterative numerical algorithm as a dynamical system, and I'm trying to leverage some tools from control system to tune the behavior of this numerical algorithm. So in the CFD world, the behaviors that are of importance, the first one is an order. So you want to have a second order scheme, or a third or a fourth order. So this is basically, what is the order of the truncated error term. And so you can write that order term, whatever order you wish, assuming you have enough degrees of freedom to satisfy this equality condition. This becomes a linear constraint on the coefficient AD. The stability of the discrete time systems comes from standard Lyapunov theory. And so this discrete time system, or the numerical algorithm, in its forward propagation would be stable if the, in this case, the L2 norm of the system matrix is less than 1. So it's a contraction or equal to 1. So if you have some, like continuity equation, that would be equal to 1. So stability is a constraint. We can treat this as a dynamical system and impose this. And this 2-norm constraint less than 1 is a convex constraint on A. This is a linear cost constraint. So we are still in the convex world. And then you want to, minimize some sort of a cost. So conventionally, the cost is, the approximation of the derivatives. So you want the derivative. So if you send a signal through this discrete derivative should represent the actual derivative in some frequency band. So you should be able to reconstruct the derivative. In the fluids, they call this a wave number, which is the frequency of in the spatial world. So we can minimize the spectral error, in this case L2. So if I do that, I get some interesting results. So here I'm trying to approximate the first derivative using an explicit formulation. And so the blue line is the accuracy of the first derivative. So the first derivative would replicate the wave number accurately up to you know, a little short of 2, and then it drops. So it's mathematically impossible to achieve, you know, full resolution up to pi. So what this means is this is the modified wave number. So this determines the granularity with which I can the size of delta x and delta t. So conventional central difference would only be, you know, matching the actual wave number up to that point and would roll off, which means you would have to go to a very small grid to make sure that the W hat is matching W. But in this optimized scheme, you can really go up to a very high value here. So which means I can go for large delta x and delta t. So I can get similar accuracy with a more granular, a coarser grid. And certain properties like first derivative, there should be no error in the real part, and there'll be no error in the imaginary part up to a certain frequency. So no phase distortion, no amplitude distortion. Now, if you go to implicit, you can get even remarkable answers. So I can really, you know, approximate my derivatives to very high frequency, which means I can make my grid very coarse and still get very good accuracy. Not only that, I can now, because this is a control problem in which I can do a weighted optimization, I can actually design finite difference schemes that have fidelity in 2 bands of the wave number. And we can kind of play around with this. And so there are some stencil size. So these are the finite difference schemes that come out of that. So the summary, I would say that, you know, if you are going the traditional route, there are also lots of opportunities to optimize and learn the schemes based on in the problem you're trying to solve. Conventionally in CFD, you know, we have a dictionary of methods and you apply them to solve the PDE. What I'm trying to advocate is you have a PDE, you know, especially, you know, if you see an unknown PDE, for example, those that are being discovered by neural network, you know, we don't have a sense of what would be the best finite difference scheme to solve it. And so a optimization framework such as this would generate a finite difference scheme to, you know, guaranteeing these errors and stability. And I think that would be quite interesting. So in summary, you know, the idea is treat coefficients of the finite difference as unknowns, and then you over-parameterize. You choose, you know, a grid size, and then you solve a, you know, an optimization problem while you're minimizing the spectral error. It is also possible to do a L1 regularization on the grid points. So that would mean that the derivative approximation are done with a sparse on a sparse grid. So, you know, I don't need data from all the grid points to approximate the derivative. It'll just pick up, you know, the sparsest set and then approximate the derivative with the spectral accuracy we need. So it'll help to think of this as a control problem in which the coefficients of the finite difference scheme is a gain, and then I can then think of all kinds of formulations from a systems perspective that this numerical algorithm needs to have fidelity in this frequency band, needs to be stable, needs to have this order of accuracy and things like that. And then we can also control transients and steady state behavior of the numerical method as well. And then it helps us to bring in uncertainty quantification. So let's say the PDE has uncertain parameters that will reflect as an uncertainty in the A matrix of the numerical method. And then we can think of methods to propagate the solution, quantifying the uncertainty or be robust to those uncertainties. And then we can think of nonlinear extensions. So what I showed you was for a linear PDE. So if you have nonlinear PDE, the discrete time dynamical system would be a nonlinear system. And then we can use tools from nonlinear control system to control the behavior of this nonlinear time marching. So I think there are a lot of nice opportunities here for applying learning techniques to come up with more high fidelity numerical methods. And then everything that I talked here are in these 2 papers, which are in JCP. The second one is still under review, but the first one is. Sorry, the second one is published and the first one is under review. So with that, I will end my talk. So if there are any questions, I'd be happy to answer.
Well, thanks for the talk. If there are any questions, please feel free to ask them directly or post them in the chat.
Yes, this is Eduardo speaking. I have a question.
Yeah.
Thanks for the talk. Very nice. You mentioned, so usually in a standard, let's say, discretization approach, AD in your case has a particular structure, right? And you mentioned one of them, maybe sparsity is one.
Yeah.
You can think about all this in a very standard way: tridiagonal, pentadiagonal, heptadiagonal, and so forth. So can you guarantee such structure for AD in that sense?
So it is a constraint on the matrix. It is a constraint on the matrix AD that you would have to impose. Now the pentadiagonal, the conventional approach is, you don't have more degrees of freedom because you don't have a mechanism to resolve these, you have fewer equations based on the order. So conventionally, depending on the order, your stencil size is controlled by it. In this case, I'm saying that go beyond the order. So if you have a second order, go for 5 stencils, because that extra degree of freedom will help you guarantee spectral accuracy.
Okay.
Otherwise, you have a fully determined equation and you get the exact answer. But if you have less equations, more unknowns, you have many solutions. That gives you an opportunity to optimize some error metric.
Okay, very good. Thank you.
Yeah.
Okay, well, thanks very much again.